What's up, Math Scholars? We're actually going to have a pretty cool Friday. We're going to do 7-4 and 7-5 together because they're really the same lesson pretty much. One is talking about exponential growth functions, which we made it with our arms off camera. So I'll just show you real quick what an exponential growth curve looks like. And then exponential decay looks like this. They use the same exact formula. They just have different growth factors. We'll talk about what that means here in a second. Who's excited for Friday? All right, so here's the formula. I actually already wrote it on the board. You don't need parentheses around the B. I don't have my parentheses around my B on the board. But we're going to label what all the pieces and parts mean in this formula. The A is going to be your starting amount. We did a bunny warm up off camera, and it was our starting amount of bunnies. I think we had 10 bunnies to start, so that's where I put the 10.
I like bunnies.
They're cute.
Yes, they're very funny.
And then B is called your growth factor. Now here's the key. If your growth factor is a number larger than 1, it will in fact be growing. But if your B is a fraction like 1/2, and it lives between 0 and 1, it would be called exponential decaying. So if I had made my growth factor, my bunny problem, a 1/2, my amount of bunnies would be shrinking every year by 1/2. So it would have gone from 10 to 5 to 2.5, and so I had no bunnies left at all.
What's the half? It's like baby bunnies.
So like for example, if I had started with 10 and then made my growth factor 1/2, every year of the scenario, I'd be losing half my bunnies.
Yes, it would be 2 bunnies and a half. What would be the half?
You can't have half a bunny, so it was a terrible example. It's a really funny word to try to say. Go ahead and try saying it. Asymptote. So if you're mad at your friend, you say, don't be an asymptote. But anyways, so let me show you our exponential growth curve that we made with our arms a few minutes ago, and our exponential decay curve that we made with our arms a few minutes ago. There's an invisible line that you can't see right now, and it acts as a boundary. So this invisible line is right here. I always draw it with a dashed line. It's right there on the x-axis, which means it has the equation y = 0. It's called an asymptote. It's a boundary line that my graph will get close to, but never actually touch. I think of it as an electric fence. You can get real close, but you can't touch it. Yep. All right, so we just have a little cute chart for you guys just to give you a picture of exponential growth, a picture of exponential decay. The intercept is normally that starting amount at A, which is interesting. B is your growth factor. There's never an x-intercept because there is that asymptote living there on the x-axis. Now, this chart doesn't have the asymptote drawn in, but I always want you guys to draw it in with a dotted line, maybe like a dotted highlighter or red marker. Yeah, it's not actually touching, it's just a terrible picture. It shouldn't ever actually touch the asymptote. Okay, it's time to get our graphing calculators rolling. So we're going to type this equation into y equals, fill out a cute little table, draw in the graph, and answer some domain and range questions. Okay. Let me get my calculator up and rolling. It's been so long since we've graphed things, huh? You hit y equals to get into where the formulas go. Somebody asked about the x. It has to be in an exponent position. So you have to use the caret key, which is above the division key. Does that make sense? So make sure yours looks exactly like mine before we head to the table.
What? Wait, where is it at?
Huh? The X button is right here beside the alpha key. All right, table time. We're going to hit our second table. I don't know what numbers you want to grab. I guess I normally start at -3 and go up to 3. So -3, -2, -1. Oh, I hit table. Have you guys ever done table? My bad if you haven't done table. So table is second graph. Second graph, because you have tables written in blue. So it's 0.59. Now mine is really blurry and hard to read on the screen. Is it a 0.88?
Yes.
Okay, so I'll just go 0.89 and I'll round it. 2, 3, and 4.5. Oh, 1.3 and then 2 and then 3. But you'll notice if you scroll around, you can scroll indefinitely on these things. It's never going to go below 0. Your graph's never going to head down into quadrant 3 or 4 because that asymptote. So I'm going to draw my asymptote in. It's invisible. I can click graph to see what I'm dealing with, but it looks like it's crossing right there at about 2. Bam. 0, 2, 1, 3.
What is E?
E? Oh, good question. Have you ever heard of pi? All right, domain. So domain is where this graph travels on the x-axis. Do you remember that? Domain is x, range is y. So this graph can go anywhere at once on the x-axis. And the way we denote that is we write negative infinity through infinity with a comma in between. I would read this to you, negative infinity through infinity. It means it can go left as far as it wants. The graph can go right as far as it wants. Have you ever seen domain written like that, or is it your first time?
First time.
This is a big day for you then, because you'll write your domain like this year in Algebra 2, in pre-calculus, and calculus. Big day, yeah? All right, let's try range. No, the range is where this graph travels on the y-axis. And if you're looking at your y-axis, the graph is never, ever going down here. So we need a way to say it's only going from 0 on up.
Okay.
So we write that 0 through infinity. 0, comma, infinity.
This is the first time I've used it.
I know. It's such an exciting day because literally we do domains and ranges like that in Algebra 2 almost every week. Where does this graph look like it's touching the y-intercept? Got 2, very good. And the asymptote is the line y equals 0. It's this line right here, y equals 0. It's a horizontal line going through all those y values of 0. That's pretty much always going to be your asymptote. All right, we get to do one that's exponential decaying now. If you look at your growth factor in the parentheses, it's a 1/3. That's going to make this shape look totally different. Instead of growing from left to right, it's going to be shrinking from left to right. We still have that caret x as our exponent. Make sure you do your caret x.
I just did X.
Yeah, when I say caret, I mean use this button to get it as an exponent. Let's look at our table of values. Maybe I'll start my table with -3 again. So -3, I'm at 81. Oh, clear the old equation, you mean? Just go to y equals, hit the clear button. So at -3, I'm at 81. At -2, I'm at 27. And you can see as I'm going, I'm getting 1/3 as big as the previous entry. See how these values are starting to shrink? They're getting 1/3 as big each entry. So what I've got here, I can only fit 3 of these on my actual picture. So my picture doesn't go up to 27. At -1, I'm at 9. At 0, I'm at 3. That's my y-intercept. At 1, I'm at 1. So it's shrinking.
I just deleted it.
You can click graph to actually see it if you want. But still got that asymptote here. It's still preventing us from ever going into a negative region. Okay?
Yeah.
I'll go ahead and click graph for our viewers at home to see the picture. But you're going to see it shrinking from left to right. Your values keep getting smaller and smaller and smaller. They're never going to go down into quadrant 4, though. The asymptote blocking the way. What do you mean? Can I see it? Okay, finally, our domain, where we can go on the x-axis, is -infinity to infinity. We can still go left and right. And our range is still 0 to infinity, because we can only go on the positive axis for our y values. X-intercept looks like it's 3. Asymptote's where it always is, at y equals 0. Oh, this is an interesting question down here. They want us to put this graph in our calculator and compare it to this graph. Any ideas what putting that negative out front would do? Guesses? Let's see. They're making some shapes with their arms. We're going to stick a negative out front and see what happens to the graph. It's pretty cool. So you can either insert a negative out front, second insert negative, or you can just type it brand new from scratch. But watch what a negative out front does. Oh my gosh. Flips the whole entire graph upside down. That's what a negative out front does. It'll flip any graph upside down. A parabola, exponential growth curve, exponential decay curve, flips it upside down. So I would just write upside down. The negative flips it upside down. That's what the negative sign does. Neil was growing a culture of bacteria for a biology experiment. He started with 23 bacteria and noticed the population increases by 40% every 90 minutes. Ooh, every 90 minutes. Normally it's like every hour. If the population continues to grow exponentially, how many will he have in 6 hours? We gotta do some thinking. The starting amount's easy. That's your A value, 23. Yep. Now here's where it gets hard. Let's think about this growth factor. We're increasing 40%. So I can't make a 0.40 be my growth factor. That's called shrinking. What do you think it would be?
4.5.
I like the 0.40 idea, but we're actually going to plop a 1 out front, and here's why. You're going to be starting with 100% of your bacteria and adding a 40% after the 90 minutes, so that's going to give you 140% of your bacteria. Does that make sense? Now this is the hard part. We got to figure out how many times it's going to double in 6 hours. So how many 90-minute periods are in 6 hours? Isn't 90 minutes an hour and a half? So let's just do 6 and divide it by 1.5, and that'll be how many hour and a half time periods there are in a 6-hour time zone. Is it 4?
Yeah.
Good. So that 4 will go here. So that's how many times the doubling will occur. Well, not the doubling, but the increasing.
So do we have to do an equation?
Yeah, I'm just going to type this equation directly in my calculator. I'm on my home screen. I'm not in the map in the graphing screen anymore. I got 26.9 bacteria. Is that what you guys got? That was a challenging one. That definitely made us think a little bit with the percentages and the 90 minutes there. Let's say in 1998 a new car cost $21,000. Its value is depreciating 15% each year. So you probably never heard of depreciation, so I'm here to tell you all about it. You're close. So we're going to start with the 21,000. It's always easy to come up with the starting amount. It's the growth factor that's a little bit hard. So depreciating 15% each year just means if I start with 100% of the value and I'm going to lose 15% of the value each year, what percent would I have next year? 85%. So my growth factor is going to be a 0.85. It's not going to be growing at all. It's going to be decaying. Does that make sense? So unlike the bacteria problem where we were adding the 40% each year, we're subtracting 15% each year. And then I think we just need to figure out how many years go by between 98 and 2005. 7 years. So there's 7 years of that 15% loss each year. Let's type it in. Very interesting. So there's a lot of reading and figuring out what your growth factor is going to be in these problems.
Wait, is it interesting or interesting?
Interesting. I say interesting. I say interesting.
I say both.
All right, we got it?
Wait, I didn't finish.
Oh, let me go back and pause for you. All right, we're going to keep it moving. We're learning a brand new formula. I think it's the last formula I'm going to teach you today. This is used anytime you invest money, like maybe in a mutual fund or a bank account, that will earn interest for you over time. So basically the bank will give you money over time. P stands for the principal, which is the original amount of money. So it's like the starting amount that we've been doing all day, the number that goes first. Your rate is going to be your rate that the bank gives you as a decimal. So for example, if they give you a 4% interest rate, you put that in as 0.04 and for R. And T is going to be your time in years. Yeah, it's pretty much the formula we just did, but they're introducing the idea of R for interest rate, T for principal, and T for time. But yeah, it's pretty much the formula we've been doing all day, pretty much. Because we have our starting amount, and we have our growth factor, and we have our exponent. All right, so let's talk Pamela here. We're going to use our brand new formula we just learned about. She's investing the $5,000, so that's the starting amount. The 12% is basically going to be a 1 plus 12%. So it really just ends up turning that growth factor into 112%. Does that make sense?
Yeah.
So it is pretty much the same formula we've been using all day. And my exponent is how many years Pamela's going to have her money in the account. Now this is awesome. If you keep money in account for a long time and they give you interest every year, some people end up being millionaires that way. Let's see if Pam is a millionaire or not. I mean, that's how retirement funds work. If your parents have retirement funds, they're hoping this is happening, that they're earning interest every year, and it's compounding and making them rich. That's what I hope my retirement fund's doing. It's high for a bank. A bank would never give you 12%, but it's not high for a retirement fund. Because retirement funds are based on the stock market. I've had a retirement fund do 12% in a year, all the time. In fact, my retirement fund last year did more like 18 or 19%. It was a really good year in the stock market. But then you have your years, so you only do like 2%. So over time, it evens out. All right, I'm jumping down just so we don't run short on time to number 15. They're having you look at a picture. They're having you decide growth or decay, so that should be easy based on shape. What do you think? So growth or decay based on the shape?
Decay.
It's decaying based on the shape. Very good. And now I'm going to talk to you about how we could come up with an equation. So we're going to use our calculator. Do you guys remember Stat World? Stat, edit. Stat, calculate. Now it's not going to be 4 anymore. It used to be 4, but now it's going to be the choice that helps us find exponential growth and decay. It's called an EXP REG. It's choice 0. So it's like a new song. Stat, edit. Stat, calculate. 0. It doesn't quite sound the same, right? Let's go ahead and try to get these numbers in. Oh, I didn't mean to do that.
Oh, no.
It's going to do it again, probably, isn't it?
Oh,
Oh my gosh. Sometimes it's happening.
What was that?
Well, I'm going to stat.
I don't know. I don't want that.
Edit. X numbers in. -1 is our first x value. 1 is our second x value. 4 is our first y value. 2.25 is our second y value. So we're getting these provided coordinates into our L1 and L2. Our x's are our L1s, and our y's are the L2s. Oh, I guess I could have put 0, 3 in. I didn't even see the 0, 3 there. So I can stick the 0, 3 in. I don't need to have all of them in, but it's a good idea.
It's not letting me delete before I put it in the wrong.
Oh, really? Now I'm going to go ahead and do the stat calculate, but choice 0 instead of choice 4, which is what we did a couple weeks ago. Now look at this. They'll give you an exponential growth equation, and they'll give you the starting amount and the growth factor. Isn't that cool? And you remember what the R values mean, right? How good of a fit that line is. And since we're dead on 1, it's a perfect fitting line. It's an equation that fits this line perfectly.
Could not have been better.
So 3 is your starting amount. What did it say the growth factor was? 0.75. Which 0.75 is 3/4 if you want to go with fraction. So it's exponential decay is what it is. It's decay. The growth factor is less than 1. Yes? All right, we're going to try another with the calculator. Is this exponential growth or decay? Good jump. Let's get in our calculator to come up with an equation that would fit this scenario. Stat, edit. All my L1s are x values, so -2, 0, 1. All my L2s are y values. 1, 4, 8. I'll let you catch up and get that in your calculator.
I don't understand.
0. Stat, edit. Stat, calculate. 0.
Oh yeah, oh yeah, oh yeah.
Is everybody trying this in your calculator?
Yep.
Okay, very good. Stat, calculate. 0. It's called the exponential line of regression. This is an exponential growth equation. Our starting amount is 4, and our growth factor is 2.
Congratulations.
Wait, what do I hear when I get calculated?
0. Choice 0. Or you can go down and... Alright, last thing I wanted to tell everybody about before they did the homework. You're going to have a couple problems in the homework where they're going to throw an equation in front of you like this. And they're going to say, do you think this, or not this equation, a chart. They're going to say, do you think this chart would be better to fit a straight line to the data or an exponential growth curve to the data? And sometimes you can tell, like see how fast this data is growing? For this one, I would definitely just go with exponential growth. So that's choice 0 if you're using Stat World. But if you see values that are going up a steady, constant amount, that's when you'd fit a straight line. And do you remember the keystrokes in the calculator in stat world to fit a straight line? Right, if the slope looks constant. If the slope looks constant, fit a straight line to it. Yeah. So you'd go stat edit, stat calculate, choice 4 if you think it's a straight line. And it's called a line, REG. Okay, so if you think it's a straight line, use choice 4. If you think it's a curved line, use choice 0. And you can always look at that R value. If your R value is close to 1, you're going to have a perfect fit line. So if you try stat edit, stat calculate 4, and your R value is not very close to 1, maybe you made the wrong choice and you should have used an exponential growth curve instead. Does that make sense?
Yes.
Okay, so I'm going to go ahead and stop the video here. Thanks for watching. That was a long video, 20 minutes, and pass homework out. Save.